All righty, let's go ahead and get started then. So before we get into the new material of today, I was asked about number 2 from the math review homework. And if I remember correctly, that one was given a certain equation, which was VF squared is V naught squared plus 2AX. We wanted to find or solve for A, the variable A. Now this equation, of course, we see in first semester physics. This is one of the main kinematics equations. And what it says is the final velocity squared is the initial velocity squared plus 2 times the acceleration times the distance traveled. It's one of the kinematics equations which we can use to calculate something we may be interested in from the system. So firstly, let me go ahead and say, just in case you weren't with me last semester, and I don't remember if I showed this at the beginning of the semester, just a little quirk of my writing is that anytime I write a V, I always put this little thing on the end there so that my U's and my V's don't look too similar, because as I start to write quickly, U and V can look very similar. And so I developed, just as I was growing older in physics, to put a little sidebar here on my V, which helps me to see that, oh, that's a V and not a U. So for these variables here, that's V with a subscript F for final velocity, and V with the subscript O for initial velocity. And so what this question is asking me to do is calculate A. Of course, this is an algebra problem, but this is an algebra problem where we really don't have a bunch of numbers everywhere. And so this is important because obviously in physics, you're left with some equation that has a whole bunch of variables, and you have to figure out how to manipulate these variables to solve for the one you want. And so that's where I talked about before, thinking about algebra not like you add, you plus 5 cancels the minus 5 and stuff like that, but rather moving things around. And so when I look at this, A is the thing I want. So that means leave A alone and move everything else over. So the first thing I need to do, because the A is stuck in this term here with 2 other things, I can't mess with him yet. But the V naught, that's over there by himself on the right side. So let me move him over to the other side. When I move him over, he becomes negative, right? He's positive on one side. If you move him to the other side, he becomes negative. So it's VF squared minus V naught squared. And what's left on the right side is 2 times A times X. I didn't mess with that stuff yet. All right, so now all I have to do is get rid of the 2 and get rid of the X to leave A by itself. So you could either do it in 2 steps, one at a time, or just realize that, you can also think of this as 2X times A, right? You just move the little numbers around. So you can move the 2 and the X over. When you move it over on the right side right now, you're multiplying. So when you move it over to the other side, it becomes dividing. So I get rid of the 2X. And so now on the other side, you're now dividing by the 2X. And on the right, all we have left is the A. Okay, and so that would be your answer. And then from here, if this were an actual problem, let's say, you look up the data in the problem, what are the numbers? And you plug the numbers into this little equation, and that'll tell you what the acceleration is. Okay, so it's an algebra equation. It's the same as if I wrote 20 equals 15 plus 2 times 10 times A. And I wanted to solve for A here. It's exactly the same thing, right? 20 equals 15 plus 20A. Okay, bring the 15 over. So 20 minus 15 becomes 5 equals 20 times A. Divide over the 20, so you get A is 5 over 20, which is 1/4. Okay, it's identical. Here we have a bunch of numbers, and for whatever reason in our brain, moving numbers or rearranging numbers in algebra is easier than if it was just purely variables. But that's because we can combine things, right? When you have 2 times 10, you can just make it 20. So now it's just one thing instead of 2 times 10. Whereas here you have 2 times A times X. Well, 2 times X looks like it's two different things, but it's really one thing. Like 2 times 10 is 20. 2 times X is whatever it is. So you just move it as one single piece of information or whatever. So that was the point of that question. Given an algebraic equation with a whole bunch of variables, no numbers, can you rearrange the equation to solve for one of the unknown variables? In this case, I asked for A. Okay. Any other questions on that?
No, sir. I got that answer, but what if you like broke it up? Like I have VF squared over 2x minus VO squared over 2x. Like I have it
That's perfectly fine.
separated.
Yeah, that's okay. That's no problem because it means the same thing, right? Yeah, that's okay.
Okay, thank you.
Sure. Yeah, it's a good question because I know your experience, everybody's experience is math class. You always have to simplify things down to the lowest simplification. And, technically you should combine it all like I have here, but I'm not a math class. I'm not a math professor. I know when I look at your answer that your answer is identical to mine. You just didn't move it into one fraction. It's two different fractions. As long as it's right, it may be written slightly differently. I can see it and I can mark it right. That's not a big deal to me. All right, so we will start into the new material, which is the beginning of the material for the semester, really, and that is thermodynamics. This is our first big chapter, our first topic for the semester, and it's a very large topic. It's a very important one, and lots of different subject areas in science make use of thermodynamics: chemistry, biology, a whole bunch of things, engineering. What we will focus on is not all of thermodynamics, but certain things that are, applicable to the real world. So there's a lot of theory and theoretical stuff we could put into this subject, but it does us no good because who cares? Rather, we will try to learn the topic making use of more real world problems that you would actually maybe see in everyday life. You may not try to answer those questions in your everyday life, but certainly things like, if I want to cool down a 6-pack of beer, how much ice should I add to the ice chest or something like this? These are questions we can actually ask and quantify and get an actual temperature. If we know how much ice we add, we know how much beer we had at what temperature, we put it all together, I can predict that after a few minutes, the beer will now be at 34 degrees Fahrenheit or whatever. So more real world type problems rather than things like, if you have an ideal gas, you have 4 moles of an ideal gas at 5 times 10 to the 5th pascals. That's all theoretical stuff. It's important, but that type of stuff, if it's going to be important for your career, you will get in those classes that teach it more thoroughly. Now, to start into this, of course, we need some of the basics, some of the foundational stuff, and a lot of it is intuition, stuff we just grew up knowing or learning over time, but we're going to kind of make it more concrete. And so the first thing to know is, what does thermodynamics actually deal with? And of course, it deals with things like temperature and heat and things like that. So first thing to know is, what is temperature? This is a very difficult question to answer. You can ask a whole bunch of scientists from different areas, and they will give you different answers that they feel is the correct answer, but is not, because it's missing something. We know deep down what temperature is. You say, well, how hot is it outside? Or how cold is it outside? Oh, it's 48 degrees. We know what we mean by this. But to actually define is very difficult because, for instance, we know what cold is, we know what hot is. But then if I ask you, is space hot or is space cold? That's a difficult question. Almost everybody thinks space is freezing cold. But it's not, okay? Not really, because one definition of temperature, which usually mostly chemists and scientists like that will use, is that it is the measure of kind of the kinetic energy of the molecules of the gas, how fast the gas is moving. Because one of the ways of knowing if something is hot or cold is based on, are the molecules vibrating very quickly or very slowly? The hotter something is, the more energetic it is, the faster it moves, the faster it vibrates. The colder it is, the slower it moves, until such time as it doesn't move anymore because it's completely cold. Okay, well, if that's your definition, well, if you go out in space, the molecules from the sun, for instance, it's spewing out a whole bunch of gas particles into space. And those gas particles are flying extremely quickly. So it's got very, very high kinetic energy. So then you'd say, okay, then it'd have to be hot, because the kinetic energy of the molecules coming off the sun, even way out far away from the sun, it's still very energetic. Yet if you put something out there, it freezes. So this definition of temperature is very difficult to nail down. And so usually what's done is you define temperature based on what it is you care about. For instance, if you're a chemist or a physicist and you're working with gases or something, or liquids, you're probably thinking temperature in the form of kinetic energy of the particles, because that's useful. Or if you're just a lay person going around, temperature is whatever a thermometer says. How do you feel? Things like this. But even that, how you feel, when you touch an object, you feel the sensation of it being hot or cold. Well, that's not a good definition at all, because, for instance, if you've ever had a fever, your body itself is extremely hot relative to its normal body temperature, but you feel very cold. You get the chills. If you put your hand on your forehead, you don't really feel the fever, but someone else comes and puts their hand on your forehead, they can feel that you're hot. Another big one, which is more useful in a classroom setting, is the fact that, let's say you're sitting in your desk, and most classroom desks are, they got the wooden table here, they got the metal bar which connects the table to the chair, and plastic chair or whatever. And those desks are sitting there all day in the same temperature. So that would tell you that every part of the desk should be at the same temperature, because it was sitting there in 68 degrees air conditioned room for a long period of time. So everything's 68 degrees. But if you go and touch the wooden part of the desk, it feels a certain temperature. And then you touch the metal bar, that feels a lot colder. Why in the world would it feel a lot colder when you know it's the same temperature as the wooden desktop? So again, there's an issue of, even in our everyday lives, what we are used to feeling for temperature and using as temperature is not a good measure of temperature at all. So let's not worry too much about it. We have our conceptual idea of temperature, and that's good enough for what we need to do. If we're going to be scientists that work specifically with temperature, then we have to be a lot more careful. But for now, We have our conceptual view, just our intuitive, what is temperature? And a better definition, generally speaking, is how much kinetic energy the gas has. The more kinetic energy, the more it's moving around, the more it's vibrating and bouncing off of other objects, the hotter it is. The other thing is heat. What is heat? Heat, that's easy. That's a form of energy. So if you remember from first semester physics, conservation of energy is a big, huge physical law that allows us to solve a lot of problems. And what it says is that the total energy of a system doesn't change over time unless it's acted upon by some outside influence. However, that energy, whatever it is, has many forms. One is kinetic, another is potential. And under the potential energy form, there's a lot of different types of potential energy. And so what can happen is one form of energy can turn into another form of energy. So for instance, the big one is you hold up a rock, it's up at some distance above the ground, so it has potential energy, mgh. You let go, gravity starts to pull it down, and as it falls, loses that potential energy because it's getting lower and lower, so the height is less and less. But that energy is converted to kinetic energy because it starts to move faster and faster, such that if you add the kinetic plus potential, it's the same number the whole time. Well, heat is just a different form of potential energy, okay? Or kinetic energy, if you want to think about it that way. But it's just energy. It's one of the ways that energy can be transferred from one object to another. And so usually the variable we use is Q, capital Q, and the units is capital J, which is of course joules. Same units as energy because it is energy. That's the units. The variable though is capital Q. Why Q? I'm not sure. Someone way hundreds of years ago, before my time, demanded that the variable for heat energy be Q. Of course, temperature, its variable is capital T, and his unit is capital K, which is Kelvin. Now, this is an issue. This is an issue because none of us use this unit when we talk about temperature. What we use here in the United States is Fahrenheit, capital F, or actually, to be more precise, degrees Fahrenheit is the unit. That's what we use in the United States. Of course, most of the rest of the world, but not all of it, but most of it uses degrees C for Celsius. However, neither of these are what we're going to use in this class. We're using Kelvin. So what we need to get straight, and by the way, Kelvin is not degrees Kelvin. It's just Kelvin. I don't know why. It's degrees Fahrenheit, degrees Celsius, or Kelvin. There's no degrees Kelvin. So we need to figure out the relationship between these three units. The one we will be using is Kelvin for the calculations, because just like units of distance have to be meters for our equations to work, or the time has to be seconds, not weeks. Same thing here with temperature. In order for our equations to work, when we get the equations, we have to use Kelvin. So the first thing we need is, of course, a way of converting between the different sets of units. So the first one we know how to do is Fahrenheit, degrees Fahrenheit, is equal to 9/5, 9/5 times degrees Celsius plus 32. Okay, and so what this equation says, it's just a conversion factor, is if you tell me the temperature in Celsius, then I can tell you what it is in Fahrenheit. How do I do it? Well, I take whatever it is in Celsius, multiply it by 9, divide by 5, and then add 32 to that number. And we can prove it. We know that the freezing point of water is 0 degrees Celsius. So if I plug 0 degrees Celsius in here, I have 9 over 5 times 0 plus 32, which of course, that's just 0, is 32. And indeed, the freezing point in Fahrenheit is 32 degrees. What about the boiling point? Does that work? Well, plug 100 in for C. Water boils at 100, so we get 9 over 5 times 100 plus 32. All right, so 900 divided by 5 plus 32. 900 divided by 5. 5 into 9 is 1 with 40, so 180 over 5 plus 32. Not over 5, I'm sorry. 180 plus 32. And 180 plus 32 is 212. And indeed, water in Fahrenheit boils at 212 degrees. So this is the conversion factor. If you know what temperature in Celsius, you could get Fahrenheit by doing this little calculation. And of course, the reverse is true. Let's say I know Fahrenheit, and I want to tell somebody in Britain what that temperature is in Celsius. Well, it's easy. Just take this equation and solve for C. It's just algebra. So F is 9 over 5 times C plus 32. I want to solve for C, so bring the 32 over. So I have F minus 32 equals 9 over 5 times C. And then bring the 9 over 5 over. So I get C then is 5 over 9 times F minus 32. And so that's how you convert. Given you know Fahrenheit, you subtract 32 from it, multiply that number by 5, divide it by 9. Okay, and that would give you Celsius. Same exact way. But, so this is what people do in their everyday lives. If you're, a news reporter, or you're reporting something and you want to tell somebody from another country about the temperature or whatever, you do this conversion. This is how you do it. Of course, you can look it up on your phone or whatever. Google, 180 Fahrenheit equals what Celsius, and it'd tell you, but what is it doing? It's doing this. Now, the important one, of course, because I don't really care about Fahrenheit and Celsius if that's not what I'm going to use in this class. The important one is, what's Kelvin? How do I get Kelvin? Well, there's good news here. The good news is, if you're used to Celsius, if you can work with Celsius, Kelvin's identical. There's only one change. And what I mean by that is this. If you think about a temperature in Celsius, and you add 5 degrees Celsius to it, okay? That's not the same as adding 5 degrees Fahrenheit. A change of 5 Celsius is different than a change of 5 Fahrenheit because of this conversion factor. 1 Fahrenheit degree is smaller than 1 Celsius degree. If you change by 1 degree Celsius, it's a bigger change in temperature than Fahrenheit. That's why Celsius goes from 0 to 100 and Fahrenheit goes from 32 to 212. There's a bigger range because each little degree of Fahrenheit is very small compared to Celsius. Celsius, if you change, it makes a big difference. Well, Kelvin and Celsius are the same change. The size of their unit is the same. So if I add 1 degree Celsius, it's the same as if I added 1 Kelvin. The only difference between them is Celsius, 0 Celsius, is 273 Kelvin. And so what's happened here is when Mr. Celsius came up with his units, his scale, he felt the important mark for his scale was water, because water is what humanity requires. That's what's the most important to humans, is water. And so he developed his scale to be relative to water. So his low point, 0, is the freezing point of water, and his upper point, let's say, is the boiling point of water. And so he made that 0 to 100. But of course, in the universe, to physics, humanity is nothing. Who gives a crap about humans? Water is nothing special. It's just another molecule out there. So then the natural scale of temperature should not care at all about water. Who cares what the freezing point of water is? Why not the freezing point of helium or aluminum? Why did I choose water? Water's not important. So what Kelvin did was he said the lowest point for this scale will be the true lowest temperature. Because obviously we've heard of negative temperature. There's, you could go outside when it's really cold and it's -5 degrees Celsius or -40. -40 is important because it happens to be, in case you don't know, it's just a little quick tip, -40 Celsius is the same as -40 Fahrenheit. They happen to be the exact same temperature for that 1 degree. Other than that, they never match. They only match in one temperature, and it happens to be -40. It's just a quirk. But so 0 is not 0 because you have negative temperatures. That's stupid. So to Kelvin, what he says is, whatever the lowest possible temperature in the universe, theoretically possible, I'm going to call that 0. And then everything goes up from there. So there's no such thing as negative Kelvin. There's 0, and then everything above 0. And of course, that's called absolute 0. Absolute 0 is defined as 0 Kelvin. That's not okay, by the way. That's 0 Kelvin. And what is 0 Kelvin relative to Celsius? It happens to be -273.15 degrees Celsius. So if I'm at -273 degrees Celsius, I call that 0 Kelvin. If I'm at -272 degrees Celsius, that's 1 Kelvin, because going up by 1 degree Celsius is the same as going up by 1 Kelvin, which is nice. We don't need a fancy conversion equation like this. All we need is the equation Kelvin is Celsius minus, or plus, 273. I'm going to skip the 0.15. That's not important to us. So if you ever want to know the temperature in Kelvin, give me the temperature in degrees Celsius and add 273 to it. And of course, the inverse is true. If you want Celsius, give me Kelvin and subtract off 273. Very easy. So that's how we're going to figure out what temperatures to use in our equations here. When we have problems and we have to plug in numbers for temperature, we have to use Kelvin. And if we don't know Kelvin, if we know Celsius, how do we get Kelvin from it? You just add 273. With that said, there's a tip. There's a little trick you can use to be easy on yourself. And the trick goes like this. Number 1 rule, every physics equation you're going to get requires Kelvin as units for temperature. However, because a change in Kelvin is the same as a change in Celsius, you could use any equation that has delta T, which is change in temperature. Like you cooled down your beer from 25 Celsius, room temperature, 25 Celsius, down to 2 degrees Celsius. So you changed a certain temperature. A change in temperature in your equation allows you to use Celsius or Kelvin. It doesn't matter. Okay, and let's prove it. Let's say we have something like this. I tell you, you're cooling off an object by 10 degrees. Okay. So let's say it went from 20 and it went to 10 degrees. And let's say that's degrees Celsius. So first thing I'm going to do is, what is delta T in degrees Celsius? Well, that's easy. Delta T is final minus initial. So 10 minus 20 is negative 10 degrees Celsius. So the change in temperature was negative 10. I reduced it by 10 in Celsius. Now let's do it. What is delta T in Kelvin? We got to be a little more fancy here. Well, if I want to do that, what I know is Celsius, and I know the conversion. If I want Kelvin, it's Celsius plus 273. Okay, so I have TF minus TO, right? Final temperature minus initial temperature. That's what delta T means. So what is the final temperature in Kelvin? Well, in Kelvin, it's whatever it was in Celsius plus 273. Okay, and so that's my Kelvin final. Minus, what's the initial temperature? Well, it's whatever it was in Celsius, 20 plus 273. That's my initial Kelvin. And so if I plug this in my calculator, I'll get my answer. But notice something. I don't need a calculator for this. Take off all the parentheses. 10 plus 273, and then minus times 20 is minus 20, minus times 273 is minus 273. So we have a plus 273 and a minus 273, they cancel out. And all that's left is 10 minus 20, which is negative 10 Kelvin. And there we go, there's the proof. It turns out that if, when you're plugging numbers in to your equation, if the equation is asking for delta T, not the temperature, but the change in temperature, then I can either use Celsius degrees or Kelvin, and either way, the number will be negative 10 or whatever the answer should be. So this is nice. This means I don't always have to convert to Kelvin if I'm smart about things. I can convert every time and be fine. So if I'm afraid that, I may use Celsius when I'm not supposed to use it, I may not know when I'm allowed to or not, then always convert to Kelvin, and that's perfectly fine. However, I personally hate having to convert if I don't have to. And so what I say is, given an equation, if it asks for temperature, I have to convert. If it asks for change in temperature, I don't have to convert. I can leave Celsius and it'll be the same number. Okay, so that's just a little trick. Oh. If you want to use it, you can use it. If not, don't use it if you're afraid you're going to make a mistake. Was there a question?
I thought you said there couldn't be any negative Kelvins.
Right. This isn't a negative temperature. Remember, what this is asking for is a change in the temperature.
Oh, okay.
So this means I've changed it by negative 10 kelvins, right? I'm not saying the temperature is negative 10. That would be wrong. You're exactly right. But this is the change in temperature. And you can have a negative change or a positive change. That's perfectly fine. Good. Very good. Any other questions so far?
What did you say about the temperature questions? One is asking for regular temperature, you convert, and then change in temperature, you leave it in Celsius?
Yeah, so just as an example, don't worry about these equations yet. We'll get to them. But one equation you might get is something like Q over T equals sigma epsilon A T to the fourth. Okay, this is going to be an equation you get later on. That is how much heat is transferred by an object because of radiation. So, you know, if you heat up a metal object really, really hot and it glows red, it's radiating light, radiating heat away. And you want to know how much heat does it radiate per second? This is the equation you would use. This says, in order to calculate it, one of the things you need is whatever the temperature of that thing is, raised to the fourth power. Don't worry about the fourth power. But here it says, give me the temperature. Oh, it's a metal pot that's at 350 degrees Celsius. Well, in that case, because what it's asking me to plug into this equation is a temperature, I have to convert it to Kelvin. If I don't convert it to Kelvin, my answer will be wrong. Separate equation. Q equals Cm delta T. Okay, and this is an equation we're going to get right up front. This is the first thing we're going to get to. This is a calorimetry equation, and this has to do with how much heat does something take in or give off because of its surroundings. So like when I said you have an ice chest, you put some ice in there and some cans of Coke or beer or whatever. And of course, the ice is going to melt and get hotter, and the beer or the Coke is going to get colder. And they're going to come to equilibrium. Well, this equation says, I don't care what the temperature is. What matters is how much did the temperature change? My beer went from 25 down to 0. So there was a change in 25 degrees. I don't care about the 25 starting and the 0 ending. I care about the difference. So for that equation, I can convert or not convert. Either way, delta T will be the same number. And so that's what I mean when I'm saying this. The first equation, there's no delta T in it. You have to convert to Kelvin. Second equation, there's a delta T in my equation. I can convert or not, doesn't matter. Either way, it'll be the same number I'm plugging in right there. If it happened to be this example in blue, then I'd either be plugging in negative 10 degrees Celsius or negative 10 Kelvin. Either way, it's just negative 10 to my calculator. And so I only mention it in case you see I don't convert sometimes, and you're wondering, why don't you convert? You said you got to be in Kelvin. It's true, it should be in Kelvin technically. But I'm using a trick of the math that a delta T Celsius is the same as delta T Kelvin, so it didn't matter whether I converted. Okay, so that's the difference. One type of equation has T, the other one has delta T. T, you have to convert because there's a big difference between 20 degrees Celsius and 293 Kelvin. Those two big different numbers. But delta T, it didn't matter. They're both the same number. Okay. Any other questions about this? And like I said, if it confuses you on when to convert or not to convert, just always convert. And then you avoid the problem altogether because converting is always right. That's actually the thing you're supposed to do. We're just trying to come up with a way of avoiding some extra work if we don't have to do it. So if it confuses you whether or not you should convert, always get to Kelvin and you'll be fine. All right. That's temperature and the units that we're using here. Now, what I'd like to do is introduce the first big topic, which I kind of did just now, and that is the topic of calorimetry. And so this is the study of heat flow. Okay. More to the point, it's the study of different objects in a system coming to equilibrium with each other because of their heat energy, their temperature. And so we know, for instance, let's say you have a glass of water and you put ice in it. You put ice in it, the ice is very cold, water is room temperature, let's say. Eventually what happens is the heat that's in the room temperature water is absorbed by the ice, warms the ice up, starts to melt it and such. And in doing so, it cools the water down, but heats the ice up. until such time, enough time goes on, that the water and the ice are at the same temperature. Okay, which is kind of weird because you say, well, wait a second, if they're at the same temperature, why in the water the ice now? Or why in the ice pure water? And that has to do with other things that we'll get to, like latent heat and how much energy is required to take away from something to make it freeze. The temperature, though, of the ice water, the water itself is at 0 Celsius and the ice is at 0 Celsius. It just so happens that the ice is solid and the water is liquid. So if you started with warm water and really cold ice, you wait a minute stirring it around, eventually everything's at the same temperature, 0 degrees, let's say. And so what calorimetry is studying and predicting, given I put these things into a system and these are their temperatures, what will the final temperature be? What will be the equilibrium temperature? So how do we do it? Well, the first thing to note is that every object takes a different amount of heat energy to change its temperature. So there's a difference between temperature and heat. Heat is the energy that you can give or take to change your temperature. And it turns out that some things you only need to give a little bit of energy to heat it up a lot in terms of raising its temperature a lot. And there are other things that you have to put a heck of a lot of energy into to try to heat it up to a higher temperature. For instance, a metal pan, you put it on a fire, it gets hot fairly quickly. But you get styrofoam and you put it on the fire and then you touch the styrofoam, you don't feel the heat. Because even though there's a whole bunch of heat entering it, that doesn't change its temperature very much. Or different types of cups. If you have hot coffee and you have a styrofoam cup or you have a paper cup, same temperature coffee goes in. Let's say the thickness of the cup is the same, but the materials being different, the styrofoam cup you can hold no problem. The paper cup gets really hot in your hand. Well, that's because the paper cup doesn't need as much energy. This is one thing. Doesn't need as much energy to change its temperature, whereas styrofoam needs a heck of a lot of energy to change temperature. Okay. And so the thing that measures how much energy is required to change temperature is called specific heat. And you can think specific because each material is different. So the specific heat of a material tells you the amount of energy required to change the temperature of 1 kilogram of the object by 1 degree. And the variable is little c, the letter C, small c. And so what is it? It's the amount of energy required to change the temperature. And now this part is important. Obviously, if you have a heck of a lot of this thing, it's going to take more energy than if you have only a little bit of the thing. So they have to standardize, and they say to change the temperature of 1 kilogram of the object by 1 Kelvin, or 1 degree Celsius, depending if you're a chemist. But we know 1 Kelvin is the same as 1 degree Celsius in terms of change. So that's how we define it. Let's say we get water, we get a kilogram of water, it's at 20 degrees, and then we start adding heat until it gets to 21 degrees. And we say, okay, how much heat did that take? 4,186 joules. All right, that's the specific heat of water. And then they get aluminum, same thing, aluminum at room temperature, 23 degrees. Okay, start adding heat. It got to 24 degrees. How much heat did you add? 300 joules. Okay, specific heat of aluminum, 300. That's all it is. Once you know that, then what we can do is say, okay, thus, if you want to know how much heat is required to change the temperature of something by a certain amount, it's equal to C, because it depends on the material, times M, how much of that material do you have? That's the mass, times the change in temperature you're trying to create. The more you're trying to change its temperature, the more heat you have to add or subtract. You're trying to heat it up, you add it. You're trying to cool it down, you take heat away. So this is our first big equation. How much energy does it require? Does something require to change its temperature by whatever delta T you want? Well, this is the equation. Now C, the specific heat, that's something you'd look up or is given in the problem, generally speaking. But if you're in a lab, you'd look up in a table, okay, this is copper. Copper has a specific heat of blah, blah, blah. And that'd just be a number you plug in. The mass, you weigh the object, figure out its mass, and plug that number in. Delta T, that's final temperature minus initial temperature. So if I were to write it out, Cm times final minus initial. That's what it looks like. And so that's going to be our first big equation. And of course, we're at the end of the lecture. So next time what we're going to do is I'll go back over this again, quickly review it, and then do some examples. And examples are fairly easy. And like I've been saying this whole time, if I put these two objects together next to each other, close off the system, so it's just those two objects, this thing's at this temperature, this thing's at this temperature, I can say, what would I predict the final temperature of the objects to be? What will be their equilibrium temperature? And I would use this equation to try to figure it out.
Oh,
Yeah, go ahead.
did you say M is the mass?
Yeah, M is mass. So how much of this thing are you talking about?
And
Right.
that's measured in kilograms?
Kilograms, just like first semester physics. That's right. Now, what you're going to see is if you're in chemistry class, you may be using CGS units, okay? And that's centimeters, grams, and seconds. And so in a chemistry class, you still have Cm delta T, but you may be using grams as the mass, and the heat may be in calories instead of joules. And so, and the temperature would be in degrees Celsius. So depending on what field you go into, you're going to be using different units.
Yeah,
And
that's
this-
how we're learning it now in general chemistry too.
Yeah,
I
it's
just
exactly the same.
explained it.
Right. It's exactly the same. It's just that, when you go look up what the specific heat of aluminum is, well, in units that have to do with calories and grams, that may be 1,000. But in joules per kilogram, it might be 4,186. Right? It's a different number you have to use. And it's just like something you don't think about, but in first semester physics, we always use acceleration due to gravity as 9.8. Well, an engineer in America, they say, no, acceleration due to gravity is 32 feet per second squared, because they're using feet instead of meters. So they use the same equations, but since their units are different, their numbers are different. So don't let the unit thing confuse you. The equations are the same, and they're going to be used the same. What may be different is in chemistry, the specific heat of water is either 1 or 1,000, depending on which units, kilograms or grams. But in physics, it's 4,186. Okay. So it's just a different constant we use, but that's the number that's given in the problem. The point in this class is, can you use the equation? That's more important. All right, so I won't keep you anymore. I know it's getting later and later. So next time we'll continue this, do a bunch of examples. I will be posting the practice problems and such to Canvas probably tonight. Obviously, we haven't gotten far into the material, so you're not expected to do it all yet, but it'll be posted for you to start using when you can. And other than that, if you have no questions, you are free to go, and I will see you next time.
Have a good one.
Thank you. Have a great day.
All right, you too.
I wouldn't
Have a
do
good
it.
day.